My name is Ted Kennedy. I am a research ecologist with the Grand Canyon Monitoring and Research Center in Flagstaff, Arizona. So my group did some synoptic food web studies from 2006 to 2009 where we described food webs throughout Grand Canyon, looking at algae and detritus and the invertebrates that eat those materials, and then the fishes too.
The Great Unconformity, discovered by John Wesley Powell in the strata of the Grand Canyon in 1869, accounts for more than 1 billion years of missing rock in certain areas. They are particular about the context of the Grand Canyon's Great Unconformity. This geological feature is a substantial gap in the rock strata, signifying a time of erosion and non-deposition, during which crucial information about the Earth's past was lost. Scientists have been perplexed by one specific absence for well over a century. Thankfully, with the development and launch of the James Webb Space Telescope, most of these mysterious puzzles are being solved. The jwst just discovered 770 trillion stars disappearing. What could this mean for humanity's ecosystem? Stay tuned, let's find out. The Great Unconformity is a prominent geological phenomenon distinguished by a rock record gap between two distinct rock strata. It denotes a period of erosion and non-deposition resulting in geological knowledge loss. The Grand Canyon is the most well-known example of the Great Unconformity, where about 1 billion years of the Earth's history are missing. This characteristic gives essential insights into geological processes and changes over long periods. Like pages in an encyclopedia, rock strata educate scientists about former ecosystems, although there are claims that this reference book needs more pages than it contains. So geologists are entrusted with comprehending what is there and determining what isn't and where it went. There are unconformities throughout the rock record, noted earth science professor MacDonald. Unconformities are simply gaps in the rock record. The Great Unconformity was so named because it was expected to be a vast, maybe a global gap. Scientists have proposed various possibilities to explain how and when this massive material was eroded. Francis McDonald, a geologist at UC Santa Barbara, and his colleagues at the University of Colorado Boulder and Colorado College think they have ruled out one of the most popular. Now here's the thing. Glaciers scraped away kilometers of rock between 720 and 635 million years ago, during a period known as Snowball Earth, when the world was covered by ice. This also explains the fast rise of worldly life soon after, during the Cambrian explosion, since this eroded debris might have supplied the seas with massive quantities of nutrients. Although analogues of the Great Unconformity may be found all over the planet with comparable amounts of rock missing from similar periods, they do not entirely match up. Could they be genuinely degraded by a global catastrophe such as Snowball Earth? Let's delve deeper. Part of the difficulty in examining the Great Unconformity is that it occurred so long ago, and the Earth is a complicated system. These rocks have been buried and eroded multiple times throughout their history, McDonald said. Fortunately, the team was able to put this idea to the test using a method known as thermochronology. The temperature starts to climb a few kilometers below the Earth's surface as you move closer to the planet's heated mantle. This results in a temperature difference of around 35 degrees Celsius for every kilometer of depth, and some minerals may get imprinted with this temperature regime. Helium-4 is created when certain radioactive elements in rocks degrade and are constantly being produced, although the percentage kept in certain minerals varies with temperature. Consequently, scientists may utilize the helium-thorium-uranium ratio in certain minerals as paleothermometer. This event allowed McDonald and his colleagues to follow how rock migrated in the crust over time, and it was buried and degraded. These unconformities are forming repeatedly through tectonic processes, McDonald said. What's new is that we can now access this much older history. The crew collected samples from granite immediately below the Great Unconformity at Pikes Peak in Colorado. They recovered zircon grains, a tough mineral, from the stone and studied the helium radionuclides inside. The approach indicated that between 1,000 and 720 million years ago, many kilometers of rock were eroded from above this granite. Notably, this period occurred before the Snowball Earth occurrences. It corresponds considerably better with when the supercontinent Rodinia was developing and breaking apart. This hints at the mechanisms that may have erased these years from the geological record. The basic hypothesis is that the formation and separation of supercontinents drove this large-scale erosion, said MacDonald. Over extended periods, the Earth's supercontinent creation and separation cycle uplifts and erodes enormous amounts of rocks. Because supercontinent activities involve much land, their impacts may emerge synchronously across the geologic record. These processes, however, do not occur concurrently, as they would in a worldwide catastrophe such as Snowball Earth. It's a messy process, MacDonald said. There are differences, and we now can perhaps resolve those differences and pull that record out. While MacDonald's findings support a tectonic origin for these enormous unconformities, they do not settle the argument. To properly constrain these occurrences, geologists must supplement our study with comparative research in other parts of the planet. The major unconformity riddle is inextricably linked to geology's other central mysteries: the rise and collapse of Snowball Earth, and the unexpected appearance of worldly life in the Ediacaran and Cambrian. Progress in any of these areas might help researchers break the case. The Earth has been subjected to major tectonic upheavals throughout its history. These upheavals created continents, sculpted spectacular mountain ranges, and shaped our landscapes. A tremendous tectonic event of unprecedented proportions occurred recently on Earth, leaving a lasting influence on our planet and its geological history. During intensive geological activity, the catastrophic tectonic event caused dramatic changes in the Earth's crust and lithosphere. Scientists and geologists from all across the globe have methodically investigated the data left behind, revealing a riveting narrative of unconceivable forces at work. The movement of Earth's tectonic plates was vital to this tectonic event. These massive chunks of the Earth's crust interact complexly as they float on the semi-fluid asthenosphere underneath them. Massive plate collisions, divergences, and transformations occurred throughout the event, producing new geological features. When tectonic plates meet, enormous pressures and forces were exerted, culminating in the construction of magnificent mountain ranges. Subduction zones formed as plates collided, with one plate driven under another. These subduction zones triggered volcanic activity, creating volcanic arcs and new landmasses. The tectonic event also demonstrated the phenomenon of continental drift, which occurs as the Earth's continents migrate gradually over geologic time. It caused continents to shift, shifting the locations of massive landmasses and rearranging the world's oceans and seas. This migration altered the world's temperature, ocean currents, flora, and animal distribution. Increased seismic activity and severe earthquakes followed the tectonic event. The impacted areas were shaken by the seismic events, which were produced by releasing stored energy along faults and plate boundaries. The force was felt across extended areas, often creating tsunamis and enormous destruction. On the other hand, extreme weathering and erosion are some natural processes that change the planet's surface over time. Weathering is the breakdown and change of rocks and minerals near the Earth's surface. At the same time, erosion is transporting and removing weathered material by natural forces such as water, wind, ice, or gravity. Harsh weathering may occur under certain situations such as extreme temperatures, heavy rain, or extended contact with chemical weathering agents. These conditions may hasten rocks' physical and chemical degradation, resulting in faster weathering. Extreme erosion may also be caused by a variety of events, including intense rainfall, high-speed winds, strong ocean currents, glacier movements, or volcanic activity. Large amounts of silt, soil, and rock may be dislodged and transported by these pressures, changing landscapes and carving out landforms such as canyons, valleys, and deltas. Extreme weather phenomena such as hurricanes, cyclones, or heavy storms may also contribute to rapid erosion by dumping large quantities of rain and creating high winds and waves. Scientists are constantly working with JWST's findings to understand all that the cosmos holds. We await more information, so stay tuned to our channel. We hope you enjoyed watching this video. If yes, we're sure you would like this next video here. Thanks for watching.